Welcome to the training session. We'll talk a bit about piezoelectric patches, their definition and its application. Well, this is the layout of the training. We will see at the end some industrial applications also. So, which is the physical behavior that makes to understand how the piezoelectric patches work? Well, piezoelectric effect was discovered in 1880. And basically, what was discovered is if you put under some pressure different kinds of material, we will see later, there is voltage induced. And this is bidirectional. If we apply some voltage in piezoelectric materials, there is vibration. So, there are several materials that can work as a piezoelectric or can take advantage of the piezoelectric effect. There are materials like quartz, which are piezoelectrics by nature. Basically, are made by silicon and oxygen. And because of the crystal structure of it, if we put some pressure, the oxygen has some negative charge and silicon has some positive. If we pressure it, the structure is modified and then there is polarity. Polarity on one side, on the other, depending if it's under tension or compression. That makes to understand how we can obtain one polarity or vice versa. There are other materials that can work as a piezoelectrics or can take advantage of this effect, which are the polycrystalline ceramics. This is the materials that are used in most of the piezoelectric patches. But these materials are ferroelectric materials. They are not polarized by nature. They are synthesized and then they need to be polarized just applying on the surface under a huge electric field. Doing that, they can be polarized and then will work as a piezoelectric material. This is an example of a polycrystalline ceramic. This middle part of the structure, when it's under pressure, is moved up and down. And regarding if it's moved up and down, the charge is positive or it's negative. What we have on the right is okay. If there is no voltage applied, there will be if there is no pressure applied to the material, there will be no voltage. But if we pressure, the polarity, the dipoles are aligned, so we will obtain voltage in the surfaces, between the different surfaces. Well, this is the electrical model of the piezoelectric patches. Indeed, the electrical model is this one. Is consists of a current source with a capacitor in parallel, and this is the resistance that we add as a load. Well, this is the characteristic, let's say, equation of the piezoelectric patch that correlates mechanical and electrical characteristics. What we can see here is that the power that we extract to our piezoelectric patch depends on the resistance on the load connected, and as you can see, there is an optimal one. Also, we can see that as more strain we put on the piezoelectric patch, we obtain higher power. Indeed, is the relationship of a square. Regarding capacitance, since we increase the capacitance, the power we extract is less. Okay, and then regarding the frequency, this is 2p frequency in hertz, we can increase the power extraction linearly. Well, this is working in not resonant frequency, so this is the case of H-Hope, because this is the resonant frequency of the piezoelectric patch, which is about of megahertz, and this is not the resonant frequency of the structural mounting, I would say. Okay. Now I will give the floor to David.
Thank you, Masaya. So Masaya has introduced to us how the piezoelectric materials has built or the natural piezoelectric materials. But let's talk about a little bit the electromechanical behavior that both are coupled, the mechanical behavior and the electrical behavior. It means that when we make pressure in a piezoelectric material, we produce an electrical field, and when you apply an electrical field to a piezoelectric material, we obtain a strain or a deformation. Okay, so the piezoelectric materials are anisotropic materials. It means that doesn't have the same behavior in all directions. In this way, there are three different main directions. Direction number one, that is aligned with the X. Direction number two, that is the Y direction. And the most important one is the Z direction and the number three direction. This number three direction is the direction of polarization. It means that the poles are aligned on this axis. Okay, the rest of the axis, 4, 6, and 4, 5, and 6 are those for shear stress. So when we start to apply an electrical field, for example, or we start to excitate in a oscillating shear stress, or we are excitating with a tensile and compression oscillating force, what we can see is that internal impedance of the piezoelectric patch has a frequency dependency behavior. There are a frequency where this internal impedance is the lowest as possible, and then there is another frequency that is very close to this first frequency, where that it's called the natural frequency of the piezoelectric patch or the piezoelectric material, okay, where the impedance is the higher one as possible. Both frequencies and the level of this impedance depends on where are you applying the force of this piezoelectric patch. It depends if you are applying on the 1 or 2 direction or the impolarization direction. Is that the one that we are look for here? So here what we are present, it's are two different piezoelectric materials. The one is called PEEK 1841 and the other one is PEEK 255. Okay, the difference is the material and the elements that constitute the crystalline framework. The both lines that are above, okay, in both graphics, represents the electrical field that a piezoelectric material could supply or could create when we apply, okay, a deformation or a strain in direction number one, that is the one that is below, okay, or in direction number 2, it means in the polarization direction. Always we could reach higher electrical fields when we apply the strain on the same direction of polarization, okay? And then what we can see here is repeated the same, okay? When we apply the deformation in direction number 1, okay, we have lower voltage than when we apply the deformation in the direction of polarization. Below, there are those voltages that we can measure if we apply a shear stress, okay? That is the gifts that are put in here. But when we talk about a specific piezoelectric patch, okay, that are here expressed, okay, we can see that the behavior depends on the frequency that we are exciting, and there are two different frequencies depending on we are exciting the strain on the one direction, that is the longest direction of the piezoelectric patch, or in the shortest direction of piezoelectric patch. More or less the voltage are the same for both directions, but the frequency, the natural frequency, changes. That is because the length of the piezoelectric patch is what measures the natural frequency of the material, okay? And the difference between both piezoelectric patch are not the material or are not the dimensions, are the thickness of the piezoelectric layer, okay? When we increase that, the number 2 and the number 5 and in this code it's related with the thickness of the piezoelectric material, not with the soft layer. The soft layer is the what that it's covering the piezoelectric material. Okay, so if we increase this thickness, what we obtain is a higher voltages. So if we use, instead of these patches, we use these patches of here, we can expect higher voltages. But with these patches of here that are thicker, what we can expect that it's the bending radius is higher. Okay, and then we can see here a different piezoelectric patch. This piezoelectric patch is a one that it's no longer selling the manufacturer, but what they do in this piezoelectric patch is to align the longitudinal direction with the polarization axis. When we align the longitudinal direction and we deform in the longitudinal direction in number 33, the axis 33, what we can see is the voltage is very high compared with the ones that are here. So always, if we can excite the strain in the polarization axis, we can expect higher voltages. Okay.
Thanks, David. Let me talk about how to modeling the piezoelectric material with finite element method. So here we just take ANSYS as the example. Use ANSYS, we can do the static analysis to study the deformation under constant force. And we can do harmonic analysis to evaluate the response of oscillation load. And also, we can do the model analysis to identify the natural frequency of the system. Last, we can do the transient analysis to examine the time-independent behavior. So here is the example. The first is the model shape we obtained from the model analysis. This one is we carry out the harmonic analysis of the PBO2 in the HO. Next, I will demonstrate the simple workflow in the ANSYS. Here, in general, there is 5 steps, or less. First, you have to define the geometry of the system. And then you have to define the material properties. And after that, you have to meshing the geometry. And after you set up everything for the numerical simulation, you carry out, you start to calculation, use the solver inside of the ANSYS, and at last, you can obtain the results. From the results, you can estimate the voltage from the piezoelectric patches and also the strain and stress of the structure bodies from the structure bodies. Here, this is the geometry we are using here to well resolve the piezoelectric patches on the spins. We have to refine the mesh of these bodies, and here is the overview of the mesh. Yeah, here we take an example of the harmonic analysis. We have to define everything here, and we have to define which one is the structure domain and another one is the acoustic domain. Then we apply the force acting on the surface of the cylinder with a different frequency. And after we define everything, and we can just input to the software, let the software to do the rest of the things. Here, okay, this is the basic results of the harmonic analysis about this, the geometry we have seen in the previous page. And we can see that the output voltage is changed with the frequency, and we can observe the peak value of the output voltage is located around maybe 8.7 hertz, and its corresponding the maximum output voltage is around 175. Here is the mode of the oscillation beam. That's all. Okay. Oh yeah. Sorry. Um, with FEM, we can do the following things. Like we can obtain uh, the output voltage on the oscillation uh, oscillation rod. Here, like we have shown in the previous, and we can obtain the string and the deformation uh, alongside the flat beam or something that we can do. Or with harmonic analysis, we can do further geometric adjustment and or material selection, and maybe we can also do the we can see what will happen if we apply the different rod acting on the cylinder.
Well, since now we have talked about the piezoelectric materials, how they are built, okay, and what are the mechanical behavior and the electrical behavior and how they are both coupled. And Gian has demonstrated how we work it in CFD simulation, FSID simulation, and an harmonic analysis. Okay, so now let's see how we, in our very fancy experimental facility, we can check and validate the experimental behavior. Okay, here in this figure, what we can see, okay, it's our simple beam that is fixed on only one side, and we have glued in both sides a piezoelectric patch. In one side, we have glued a piezoelectric patch that is the higher one, okay, that covers around 60 millimeters by 40 millimeters, more or less, okay? And this piezoelectric patch of here, the polarization direction is transverse to the plane of the piezoelectric patch. But in the other side, okay, it's a small piezoelectric patch, and the polarization direction is in the same direction of the beam. We use one of them to excite the structure, and the other one that we use it's just to read and measure the output voltage in open circuit. Okay. For other applications, what we use is a different loads, electrical loads, and we can reach which is the highest output power possible related with the electrical power. So let's see a short video. Okay, what we will see in this video. First of all, what we will see in this video is our beam, okay, that it's oscillating. And also what we will see are where are placed both piezoelectric patches, that both are this is one, it's the smallest one, okay, and the other one is the biggest one. The smallest one, remember that is the one that the polarization axis is inside the plane of the piezoelectric patch, okay. One of them that we use is to excite, and the other one is to measure the output voltage. We are also measuring the displacement with a laser sensors on the top tip of here, and other two are in both sides of the cantilever beam. Okay. Now what we are doing here is make a sweep from low frequencies to high frequencies, meaning low frequencies below the natural frequency of the system and high frequencies above the natural frequency of the system. The natural frequency of this system is more or less around 6.4, 6.5 hertz. It depends if we use here the shaker or not. Firstly, we use the shaker, but just was only to excite the torsion modes of this beam. But now that we are only want to work with the beam modes, okay, we just use the ones that are excited with piezoelectric patch that is exactly in the symmetric axis. Okay, now what we can see here is with the oscilloscope where are the excitation signal, okay, that is the blue one, and the measured signal. As we increase the frequency, what we will be able to see is the green signal, that is the output voltage, will be increased up to reach the highest output voltage that can be reached, okay, and then will be decreased. And the image that is below is the spectrum. So in green, we will be that this peak of here will be very short and will increase the contribution. Okay, let's see that here, that we can see that it's increasing the output voltage. And another thing that we can see is that there are a little time difference between peaks of the excitation voltage and the output voltage. This means this is due to the hysteresis implicit in piezoelectric materials. Okay, let's see here above, okay, that peak, and now the green one will goes down, goes down, goes down as the amplitude is reducing. Okay, let's see, and now it's smaller, and in the next time window we will see that this peak of here it's also decreasing in it.
Okay, thank you very much for these very interesting presentations about the behavior of these type of materials. So now I will end this lecture just describing several industrial applications which are very, very interesting. So here you can see, for instance, in the automotive sector, there are recent developments which have focused on integrating these piezoelectric patches into components like the tires and the shock absorbers in order to convert the mechanical stresses and the vibrations into electrical energy that then it's intended to be used to, for instance, enable self-powered sensors and enhance overall energy efficiencies in vehicles. For example, there is a company, Goodyear, who is already developed a prototype tire which will be built with integrated piezoelectric patches in order to take profit of this harvested energy. Another very interesting application related to the previous one are the smart infrastructures. And there are in many cities which are planning to use piezoelectric patches in roads and bridges, for instance, to harvest energy from the oscillating pressures induced by the vehicles that circulate on them. And with this energy, they are planning to power streetlights, for instance, or feed road sensors. For instance, there are two cases. There is a project in Israel that intends to generate electricity from the traffic. And also in California, United States, there is California's Energy Harvesting Roadway project, which wants to feed the street lines from this type of energy. Another application is the industrial machinery and manufacturing, and all the machines nowadays will have the possibility to have piezoelectric patches attached to them in order to capture all the vibrations induced by their operation and convert them into electrical energy in order to power sensors, for instance, for condition monitoring of the machine health status. And based on these signals, it will be possible to carry out predictive maintenance on this type of industrial machinery. As an example, General Electric has already vibration-powered sensors in order to monitor factory equipment without the need for an external power supply. And also another company like Siemens is also using self-powered wireless sensors to monitor equipment health, enhancing the efficiency and reducing the downtime due to unexpected failures. There are more things, very, very interesting, like the objective of develop what they call wearable technology. And in this case, for instance, some companies are planning to integrate piezoelectric materials into wearable devices which can harvest energy from, for example, human motion, and powering sensors that monitor our health, or for instance, the condition of a worker, and also the environmental situation where he is developing his job. In this case, we have some companies which have already developed flexible piezoelectric sensors for self-powered monitoring of physiological signals in hazardous work environments in order to protect the workers. And since a long time ago, one of the most important applications of these piezoelectric patches is obviously the aerospace industry, which is exploring the use of piezoelectric materials to harvest energy from the vibrations, aiming to power sensors and reduce the wiring, thereby decreasing aircraft weight and improving fuel efficiency. For instance, you can see here that inside the slats, they are trying to install this type of piezoelectric systems in order to harvest the energy. And obviously, we couldn't forget our application, which is one of the newest ones in the field of fluids, incompressible fluids like water, which is the harvesting of hidden hydro energy in water networks, which is the objective of the H-Hope project. And obviously, the idea is to strategically place cylinders within water pipelines, for instance, or open channels or open streams, induce vortex-induced vibrations from which we could harness electricity in order to use it, for instance, to feed sensors. This is a sustainable solution as it will provide a renewable energy source by tapping into existing water flows. It intends to be an efficient energy harvesting technology, as it will offer a low-cost solution for energy recovery in low head and small water bodies. And obviously, if we can fit sensors with it, we will achieve enhanced monitoring, facilitating the digitalisation of water networks by powering Internet of Things sensors and leading to improved management of water streams and the detection of leaks. And here you can see a video where we can observe the generation of vortices behind one of the harvesters of the project, which will induce vertical vibrations on this body, and thanks to some piezoelectric patches, we will be able to extract the hidden hydro energy in a particular flow condition. So thank you very much for your attention, and obviously if you have questions or interest in our research, please contact us or visit the H-Hope project website, www.hope.eu. Thank you.